A driven electrode, according to the National Fire Protection Association Electrical Inspection Manual, is a ground rod made by driving it into the earth. Driven electrodes serve the crucial function of creating a low resistance path to the earth for electrical current. This functionality is essential in several key applications. Firstly, they provide grounding for electrical systems, ensuring a safe path for fault currents to flow back to the source, thereby minimizing the risk of electrical shock and equipment damage. Secondly, driven electrodes offer protection against lightning strikes, diverting the immense energy of a lightning strike safely into the ground, preventing damage to structures and electrical equipment. Thirdly, they are used to dissipate static electricity, preventing the buildup of static charges that can damage sensitive electronic components or create fire hazards. Driven electrodes are commonly made of materials like copper, steel, or stainless steel, chosen for their conductivity and resistance to corrosion. Installation typically involves driving the electrode vertically into the ground using a sledgehammer or a mechanical driver. The depth to which the electrode is driven is a critical factor, depending on the local soil conditions and the desired resistance level. Soil composition, moisture content, and temperature all influence the soil's resistivity, which in turn affects the overall grounding resistance. After installation, testing is essential to verify that the driven electrode provides a sufficiently low resistance path to the earth. This is typically accomplished using a soil resistance tester, also known as a ground resistance meter. This instrument measures the resistance between the electrode and the surrounding soil, providing an indication of the effectiveness of the grounding system. The term made in the context of the NFPA Electrical Inspection Manual emphasizes that a driven electrode is physically created by driving it into the earth. This distinguishes it from other grounding methods, such as electrodes embedded in concrete or buried in the ground. The resistance of a grounding electrode is crucial for ensuring electrical safety and proper equipment operation. A low-resistance ground provides a safe path for fault currents, minimizing the voltage rise on grounded equipment and reducing the risk of electric shock. In addition to the single ground rod, the NEC National Electrical Code permits the use of multiple ground rods bonded together to achieve the desired resistance to ground. NEC Section 250.53 A3 specifies the requirements for supplemental electrode grounding. This section stipulates that a single ground rod electrode must have a resistance to ground of 25 ohms or less. If the single ground rod resistance exceeds 25 ohms, a supplemental electrode is required. The supplemental electrode must be bonded to the original ground rod. The purpose of the supplemental electrode is to lower the overall resistance of the grounding system. Common supplemental electrodes include ground plates, ground rings, or additional ground rods. The NEC outlines specific requirements for the size and type of grounding electrodes, as well as the methods for bonding them together. Proper installation and bonding are crucial to ensure the effectiveness of the grounding system. Furthermore, the NEC mandates regular inspection and testing of grounding systems to verify their continued effectiveness. Periodic testing helps identify any deterioration or damage to the grounding electrodes or bonding connections. Maintaining a low-resistance ground is essential for protecting people and equipment from electrical hazards. The choice of electrode material is influenced by several factors, including soil corrosivity, cost, and conductivity requirement. Copper is a highly conductive material commonly used for grounding electrodes, but it can be susceptible to corrosion in certain soil conditions. Steel is a more cost-effective option, but it may require corrosion protection, such as galvanization, to ensure long-term performance. Stainless steel offers excellent corrosion resistance and is often used in harsh environments. The size and length of the driven electrode also affect its resistance to ground. Longer electrodes typically provide lower resistance, as they have a larger surface area in contact with the soil. The diameter of the electrode also plays a role, with larger diameter electrodes generally offering lower resistance. Soil conditions significantly impact the performance of driven electrodes. Sandy soils tend to have higher resistivity than clay soils, requiring longer or more numerous electrodes to achieve the desired resistance. Moisture content is another critical factor, as dry soils have much higher resistivity than moist soils. The presence of salts and other minerals in the soil can also affect its conductivity. Proper grounding is essential for protecting sensitive electronic equipment from damage due to voltage surges and electrical noise. A well-designed grounding system provides a stable reference point for electronic circuits, minimizing the effects of voltage fluctuations and electromagnetic interference. In addition to safety and equipment protection, proper grounding is also important for ensuring the reliable operation of electrical systems. Ground loops, which occur when multiple ground paths exist, can cause circulating currents that interfere with electronic signals and create noise in audio and video equipment. A properly designed grounding system minimizes the risk of ground loops and ensures clean, noise-free signals. Grounding systems are often used in conjunction with surge protective devices, SPDs, to provide comprehensive protection against voltage surges. SPDs are designed to divert surge currents to ground, preventing them from damaging sensitive equipment. A well-grounded system provides a low-impedance path for these surge currents, maximizing the effectiveness of the SPD. The NEC provides detailed requirements for the installation and testing of grounding systems. Compliance with these requirements is essential for ensuring the safety and reliability of electrical installations. Regular inspections and testing of grounding systems are crucial for identifying any potential problems and ensuring that the system continues to perform as intended. Grounding is a critical aspect of electrical safety and should not be overlooked. A properly designed and installed grounding system protects people and equipment from electrical hazards and ensures the reliable operation of electrical systems. Driven electrodes play a vital role in grounding systems, providing a low-resistance path to the earth for electrical current. Understanding the principles of grounding and the proper installation and testing of driven electrodes is essential for anyone working with electrical systems. In addition to driven ground rods, other types of grounding electrodes are available, each with its own advantages and disadvantages. Concrete encased electrodes, also known as UFA grounds, are installed within concrete foundations and provide excellent grounding performance due to the large contact area with the earth. Ground plates are buried horizontally in the ground and are often used in areas where it is difficult to drive ground rods. Ground rings consist of a bare copper conductor encircling a building or structure and buried directly in the earth. These rings provide a low-impedance ground path and are often used in conjunction with other grounding electrodes. The selection of the appropriate grounding electrode depends on various factors, including soil conditions, available space, and the specific requirements of the electrical system. A qualified electrical engineer or electrician can assess these factors and recommend the most suitable grounding solution. The NEC provides guidance on the selection and installation of different types of grounding electrodes. It is important to consult the NEC and follow its requirements to ensure that the grounding system meets all applicable safety standards. Improper grounding can have serious consequences, including electrical shock, fire, and equipment damage. Therefore, it is essential to take grounding seriously and to ensure that all electrical systems are properly grounded. Regular inspections and testing of grounding systems can help identify any potential problems before they lead to accidents or equipment failures. A proactive approach to grounding maintenance is essential for ensuring the long-term safety and reliability of electrical installations. The resistance of a grounding electrode can be affected by several factors, including soil temperature, moisture content, and the presence of corrosive substances. In cold climates, the soil can freeze, increasing its resistivity and reducing the effectiveness of the grounding electrode. During dry periods, the soil can lose moisture, also increasing its resistivity. Corrosive substances in the soil can attack the grounding electrode, reducing its cross-sectional area and increasing its resistance. To mitigate these effects, it is important to select grounding electrodes that are resistant to corrosion and to ensure that the soil around the electrode is well drained. Periodic testing of the grounding electrode resistance can help identify any changes in its performance and allow for corrective action to be taken. If the resistance of the grounding electrode increases significantly, it may be necessary to replace the electrode or to add additional electrodes to the grounding system. The use of ground-enhancing materials, such as bentonite clay, can also help to improve the performance of grounding electrodes. These materials are designed to increase the conductivity of the soil around the electrode, reducing its resistance to ground. Ground-enhancing materials are particularly useful in areas with poor soil conditions, such as sandy or rocky soils. The NEC requires that all grounding electrodes be properly bonded together to create a low-impedance ground path. Bonding is typically accomplished using copper conductors, which are sized according to the size of the electrical system. Improper bonding can create high-impedance ground paths, which can increase the risk of electrical shock and equipment damage. It is important to ensure that all bonding connections are clean and tight and that the bonding conductors are properly protected from corrosion. The NEC also requires that all metal enclosures and equipment be properly grounded. This is typically accomplished by connecting the metal enclosure or equipment to the grounding electrode system using a grounding conductor. Grounding metal enclosures and equipment helps to prevent electrical shock and to protect equipment from damage due to voltage surges. In addition to grounding for safety, grounding is also important for electromagnetic compatibility (EMC). A properly grounded system can help to reduce electromagnetic interference (EMI), which can disrupt the operation of electronic equipment. Grounding for EMC typically involves creating a low-impedance ground plane and shielding sensitive electronic components. The design of a grounding system for EMC can be complex and may require the expertise of an EMC engineer. Grounding is a critical aspect of electrical engineering and should be given careful consideration in the design and installation of all electrical systems. A properly designed and installed grounding system protects people and equipment from electrical hazards, ensures the reliable operation of electrical systems, and reduces electromagnetic interference. The NEC provides detailed requirements for grounding, and it is important to consult the NEC and follow its requirements to ensure that the grounding system meets all applicable safety standards. Driven electrodes are just one component of a comprehensive grounding system. The effectiveness of a driven electrode depends on various factors, including the soil conditions, the depth of installation, and the material of the electrode. Regular testing and maintenance are essential to ensure that the driven electrode continues to provide a low-resistance path to ground. In addition to driven electrodes, other types of grounding electrodes are available, such as plate electrodes, concrete encased electrodes, and ground rings. The selection of the appropriate grounding electrode depends on the specific application and the site conditions. A qualified electrical engineer or electrician can assess these factors and recommend the most suitable grounding solution. The principles of grounding are based on the fundamental laws of electricity. Understanding these principles is essential for designing and installing effective grounding systems. The National Electrical Code (NEC) Article 250 provides comprehensive requirements for grounding and bonding. Compliance with Article 250 is mandatory for all electrical installations in the United States. The purpose of grounding is to provide a low-impedance path for fault currents to return to the source. This low-impedance path ensures that the overcurrent protective devices, such as circuit breakers and fuses, will operate quickly to clear the fault. Without proper grounding, fault currents may not be sufficient to trip the overcurrent protective devices, which can lead to overheating, fire, and electrical shock. Grounding also helps to stabilize the voltage on electrical systems. By providing a reference point to ground, grounding helps to minimize voltage fluctuations and transients. This is particularly important for sensitive electronic equipment, which can be damaged by voltage variations. Grounding also helps to reduce electrical noise. Electrical noise can interfere with the operation of electronic equipment and can cause data errors. By providing a lower impedance path to ground, grounding helps to shunt electrical noise away from sensitive circuits. The design of a grounding system should take into account the specific characteristics of the electrical system and the site conditions. Factors to consider include the size of the electrical system, the type of equipment being used, the soil resistivity, and the presence of underground utilities. A qualified electrical engineer or electrician can perform a grounding study to determine the optimal grounding system design. The installation of a grounding system should be performed by a qualified electrician. The electrician should follow all applicable codes and standards and should use appropriate materials and methods. After the grounding system is installed, it should be tested to verify that it meets the required performance standards. The testing should be performed using calibrated test equipment and should be documented in a written report. The grounding system should be inspected and tested on a regular basis to ensure that it continues to perform as intended. The inspection and testing should be performed by a qualified electrician and should be documented in a written report. Grounding is an essential aspect of electrical safety. A properly designed, installed, and maintained grounding system protects people and equipment from electrical hazards. It also ensures the reliable operation of electrical systems and reduces electrical noise. Remember that mate in the NFPA Electrical Inspection Manual means physically driving the electrode into the earth.